Hello everyone and welcome to the second part of Darcy law. So, in this we would be further discussing the Darcy law, how it can be applied, in which conditions we can apply and so on. So, let us see that as we have discussed in Darcy law, that hydraulic conductivity is a very important factor here. So, in the metric system or metric units, hydraulic conductivity is defined as rate of flow in cubic meters per day through a cross sectional area. So, in earlier systems there used to be a cubic feet per day and so on, though cubic meters per day can be converted into other values also, but normally this is what we follow in metric system, that the hydraulic conductivity is defined or measured in the cubic meter per day through a cross sectional area. In case of our earlier discussion, it is A on 1 square meter, and that is cross sectional area would be represented as square meter under a hydraulic gradient, that is HL upon L is 1 meter per meter to the prevailing kinematic viscosity. So, whatever the viscosity is there, as per that it would be considered in metric system. Now, when we go for estimations of Q and K and other things through this numerical analysis or in questions, then all these parameters will become very important, especially their units. So, when a question comes about the finding out hydraulic conductivity of a aquifer and other values are given, then the first thing we have to do it, that convert everything in the metric system and be careful about whether it is a cubic meter or or meter square, and it is whether per day or per second, that kind of thing we have to be very careful while calculating all these things. So, in your assignments and in your final examinations also, these things might be there, such questions, and one has to take care about the units in metric system. So, the term, as you know, that we have in earlier discussion we have little touched about this, that the term permeability is used to express the general water transmissive character of the rocks. And because now we are instead of experiment setup, now we are slowly moving towards the real situation that water is flowing through rocks. So, this permeability term we can express as the general water transmissive character of the rocks. So, changes in temperature will also affect our hydraulic conductivity, and whatever the water bearing materials or chemicals or even small particles of clay size or even less than clay size might be there, they too will affect our hydraulic conductivity through this viscosity of the fluid which is flowing. In our case it is water. So, to the formula to convert hydraulic conductivity at different temperatures can be like KT, that is hydraulic conductivity at temperature T, can be equal to KL VL upon Vt, and this nu is the symbol in Greek which is which I have just mentioned V, but it is basically denoted as nu. So, in this PPT it might be looking V, but it is considered as a nu because this is what we follow. And KT, that is hydraulic conductivity as standard temperature or the begin temperature is given. Hydraulic conductivity at laboratory temperature, that is the KL, and hydraulic conductivity or kinematic viscosity which is nu of water at laboratory temperature and standard temperature respectively. So, these two values nu L and nu T are used in that manner. So, if we there are certain standard tables are there for a temperature. So, a conversion factor at 60 degree Fahrenheit about the hydraulic conductivity with different temperature is shown in this table. So, if I consider that temperature is 70 degree Fahrenheit, it can also be converted into centigrade, no problem. So, the conversion factor the Vt would be 0.87. So, here also you can see that when temperature is less, in terms of degree Fahrenheit in this example, then Vt is going to be more. So, and when temperature is more, the Vt is going to be, or nu T is going to be less. So, most rocks are as we know not homogeneous and neither uniform in nature, and they are within a one type of rock. Suppose if I give the example of very common rocks in which we consider in our examples, that is sandstone. So, even a sandstone bed or layer will not have a completely uniform character, neither it would be homogeneous. So, that is why many times in a real situations in groundwater engineering, this non-uniformity of rocks or heterogeneity, the character of the rock plays very important role and makes our estimations little wild. So, one has to be very careful while considering the real situations. So, because of a non-uniform and heterogeneous of rocks, heterogeneous character of rocks, the result of natural variations during their formation is happens because different rocks are formed at different time and different environmental conditions too, and therefore, these variations will also be there. So, as a result of natural variations I have just said that might be the age variation, might be the temperature variation or overall environmental variation during their formation and later on subsequent alteration, especially alterations which we see or manifested at the surface of different rocks, and they are heterogeneous. Their properties are vary from one place to another within one rock. So, a one rock layer cannot always be considered as uniform or homogeneous. That is the main point here. So, now there are two types. One is the one type of heterogeneity or homogeneity if we want, and then it is a vertical heterogeneity, and another one is of course the horizontal heterogeneity. So, these two exist all the time in all types of rocks. If I give the example of granitic terrain, a batholith. So, on the top part you may have some weathering, that is alteration, fractures, and some gaps are there in rocks, and you may have a possibility of flowing water, that is in unconfined aquifer condition. So, in such cases the vertical heterogeneity and horizontal heterogeneity will definitely exist. Similarly, in other types of rocks, similar kind of situation might be seen in the field. So, if I take the example of vertical heterogeneity, so like these are the layers which are shown here: sandstone, shale, sandstone, shale, sandstone. This is a very common sequence of sedimentary terrain you can find in groundwater conditions like this. So, sandstone is more favorable from groundwater flow movement, but shale is not, because in sandstone you are having good porosity, you are having good permeability, but in shale you might have good porosity, but you may not have permeability. So, vertically these are heterogeneous. So, it is easier for water to flow between the shale layers than across them, because they are not. So, that will that is also indicating that therefore, there are horizontal heterogeneity also. So, the sandstone and shale layers may individually be isotropic, simply one single layer, but the horizontal permeability of combination of beds is greater than vertical permeability. So, these two, vertical and horizontal, will also vary depending on the geologic condition, subsurface geologic condition. Even within a single rock type, platy grains, that means the grains which are flat in character, not rounded or subrounded. So, platy grains tend to be deposited with their longer axis horizontal, and geologists use or sedimentologists use these orientation of these platy grains to find out what was the flow conditions during the deposition of such rocks. Anyway, so here these platy grains tend to deposit it there along their longer axis, and therefore, the texture causes permeability and isotropy, and although the rock may be homogeneous. So, this kind of situation may also be encountered if we look very carefully even an individual layer of different rocks. So, equality of properties in all directions at a point is isotropy, which in our case is that everywhere it is same, but in in nature it is not like that. So, whereas the variation of properties with direction is anisotropic. So, most of the rocks are heterogeneous in character horizontally, vertically. Most of the rocks are not isotropic, they are anisotropic. So, most sedimentary rocks are anisotropic with respect to permeability because they contain grains, not only with respect to permeability, I would also add the with respect to porosity as well. So, porosity is permeability is affected by porosity. So, that most of the rocks are having different variations contains because of different grains which have been used to form these rocks and we are not spherical. So, if there is a platy grains, they will have different behavior from the groundwater point of view. So, now come back to again our Darcy law, and whatever we have discussed, now we will try to link all these things. So, as we know that groundwater or water in every condition flows from high to low elevations. So, in groundwater conditions, or more precise what we can say that from high potential energy, that is hydraulic head, to low potential energy water flows. And it is also shown on the right figure that the flow direction of water is like this. So, water is flowing from high potential region to low potential region, and HL or delta L is also shown here. So, here the height is here, it is the here. So, delta L is also shown. So, on surface you may not see any signatures of such a hydraulic head which is observed through these two tubes or in real situation two bells, but this is what, and this blue part is of course this is showing the water table, the depth of water level or water table if we think in terms of above mean sea level. So, this part is definitely completely saturated with water, that is why this blue line is showing our water table, and the top part is unsaturated, it is not there. So, now we are having, if we go for 3D calculation kind of thing. So, we are having Z here which is the thickness of the this saturated horizon, and then we are having the Y which is the length of saturated horizon. So, here the H is shown here is the delta H is shown. So, this is hydraulic head, that is the change in the hydraulic head, and the distance in the direction of flow, that is L is here. So, the groundwater, as we know, we have discussed, will flow from high elevation to low elevation and from high potential energy point to the low potential energy point. So, the hydraulic head is measured by determination of vertical position of water table, which we are doing in this setup or in this figure through tube say X or well X and Y. So, the hydraulic head is measured by determination of vertical position of the water table in well related to the reference surface, and reference surface here is for us is above mean sea level, not from topographic surface, because topographic surface may mislead and you may get this hydraulic head value little wrong. So, always convert water level to water table. So, Darcy law, as we have seen, as an empirical equation, and that describes the flow of fluid through a porous medium. Porous medium, it is do not think all the time that we are encountering in real situations the only sedimentary rocks, because in case of sedimentary rocks, these are you may have lot of sedimentary rocks are porous. But when we say porous medium, in case of igneous rocks or metamorphic rocks, we mean here we are having some weathered zone, we are having some fractures, and interconnectivity is also there, some joint planes and other things. So, through these openings, maybe less than millimeter openings or millimeter openings, the water can flow, maybe slower than even a coarse grain sandstone, does not matter. So, that also considered as a porous medium. So, this word porous medium is not only applicable in case of sedimentary rocks, but also applicable to igneous and metamorphic rocks. So, this Darcy law was formulated by, as we have already discussed in the first part of this Darcy law discussion, by the Henry Darcy, based on the results on the experiments which we had done in the lab on different kind of sands and clay and fine sands, coarse sands, and through this experiments a empirical relationship was found, and this was in the 19th century by a French engineer. Now, what Darcy law says? It says that the discharge Q is proportional to the gradient in the hydraulic head and the hydraulic conductivity. So, we have already written in the previous discussion that Q equal to K A H L upon L. Now, the same equation we can write also like this. So, here what we are bringing, the delta H here we are writing, and delta L we are also writing in the length. So, this will give us a total discharge, and there will be a minus also value will be there. So, Q equal to total discharge cubic liter per time, and so maybe minute or minute generally it is used here. Whereas K is the hydraulic conductivity, that is liter per time, and L is the distance in direction of flow, and in here it is the shown as L. So, we can the equation 1 writes that Q equal to minus K A delta H upon L. The same equation can also be written in case of specific discharge as Darcy flux is, that is small q equal to minus K delta H upon L. So, here we can write that the view equal to minus K delta H upon N E and H L. So, what is this Q is specific discharge. So, instead of now that is total discharge, we are talking about specific discharge, which is denoted here henceforth as small q, and of course, A is our always cross sectional area. So, here A is cross sectional area, that is L square length square, and here H is the hydraulic head L. Earlier I mentioned the liter or other things, sorry, this part is length, L is the length here, not a liter per minute or per second. So, that just remember that correction, and NE equal to the effective porosity, which is a dimensionless quantity. So, likewise the same equation can be written in a different way, and we can get different outputs from them. So, now as we can see that for total discharge, this equation can be used. For a specific discharge, that is Darcy flux, can be used. The seepage velocity, average linear velocity, equation 3 can be used. Now, the validity and limitations of Darcy law. No equation, no relationship, neither empirical, stochastic or any other kind of relationships are flawless. That means every equation will have limitations, nothing is perfect, because like if I take the example of Darcy law, it is empirical relationship based on certain experiments which have been done. So, in the labs. So, the validity will be also that what I am trying to say, that in every conditions Darcy law cannot be applied. So, there are limitations of Darcy law, or where the Darcy law will be valid. So, Darcy law can be applied to many situations, but do not correspond to these assumptions. What are assumptions? Unsaturated and saturated flow. There we are having problem that within a rock formation, if we are having this situation, flow in fractured rocks and granular medium, again these equation assumptions are there, and the transient flow and the steady state flow. So, this is again one of the assumptions, that the whatever is being flowed, it is transient, it is not, may not be continuous transient flow on that moment, and the steady state means the as it is flowing, and whenever you are doing any kind of estimations, things are not changing. flow in acutars and aquifers. That is also assumed here, and flow in homogeneous and heterogeneous systems. And we have already discussed that in this real world nothing is homogeneous, and there are heterogeneities vertical and horizontal, but here it is assumed. So, that the Darcy law is a physical principle or an empirical relationship which is applied to most of the groundwater. In most of the conditions you can apply. However, in certain conditions which we are going to discuss, Darcy law cannot be applied. For example, I will just touch, and later on we will have more detailed discussion about laminar flow and turbulent flow. So, there in turbulent flow Darcy law is not valid. So, Darcy law is not universal, and basically no law in fact universal in only for certain conditions. If it is being assumed or fulfilled, then it will be applicable. So, not universal and having few limitations. So, Darcy law can be inappropriate if the flow velocity is too great in a medium with large pores. There Darcy law is not applicable. So, in a normal conditions when flow rate is not very high, then Darcy law will apply, but if it is not there, then Darcy law is not applicable. So, Darcy law assumes or supposes that a flow is in laminar fashion, that we will discuss what is laminar and what is turbulent, and also valid when Reynolds number. Now, this number we will also be discussing. So, this Reynolds number is less than 1, then only, and this we are talking in groundwater conditions, subsurface conditions, not in overground conditions. So, Darcy law assumes that the flow is laminar and the Reynolds number is 1 or less than 1. The upper limit can be extended up to 10. So, the Reynolds numbers upper limit can also be extended, but slowly the estimations may go wild if we go beyond 1. So, these are the few limitations. So, where Darcy law can be applied or not. So, before that we will see that what types of fluid flow are there. So, there are different conditions, different fluid flow conditions might be there. So, let us take one, the first one, the left top left one, which is the steady and unsteady flow. One type of flow are possible. The second is laminar and turbulent flow. In these conditions also how things varies. Third one is the uniform and non-uniform flow, and fourth one is the rotational and irrotational flow are also there. Fifth one is the 1, 2 or 3 dimensional flow, and sixth one is the comprehensible and incomprehensible flow. So, flow can be of different types, steady, unsteady, flow can be uniform or non-uniform, flow can be laminar and turbulent. So, that means in all these variations Darcy law cannot be applied, only in, as we have seen that in case of laminar flow Darcy law apply. So, now let us bring the discussion on this laminar and turbulent flow. So, in there are two flow conditions which is assumed, and that one is the laminar and another one is the turbulent. If water is flowing in a laminar fashion through a laminar flow, then the I would say that the procession of water grains is very smooth, orderly procession, that this water moves through a channel or in subsurface conditions in a very orderly fashion. Whereas, in case of turbulent flow there is no order, and grains of individual water grains mixes with other either in horizontally or vertically, and therefore, the water becomes turbulent, as shown here also, that this is a smooth procession of water grains in a orderly fashion in the case of laminar flow, whereas in case of turbulent flow this smoothness is not there. So, they are crisscrossing different layers or paths of water grains movement, and therefore, the flow becomes turbulent, and once the flow becomes turbulence, then Darcy law is not valid. So, that laminar flow, as I have just said, is having an endless procession of water particles following the same path. Now, let me give you one example. In a real life situation you might have seen in many rivers or in especially in canal systems, the design is such that the water should always flow through a laminar fashion. There should not be intermixing of different layers of water or different grains of water. And if water flows through a channel which is a laminar, then there will not be erosion and your system will last for very long time. I will give you the example like of Upper Ganga Canal. In most of the stretch of Upper Ganga Canal, the design is like that, the discharge is maintained like that, the suspended particles are maintained like that the most of the time in most of the stretch of Ganga Canal, the water flows in a laminar fashion and therefore, all estimates goes very well. But there are situations where there are some locations within this system that the water might not be flowing in a laminar fashion. So, there the lining of canal is required and it has been done. There you can see on the ground also when you see that the sometimes you do not feel that whether water is really flowing or not if there is a floating object is not there. So, that laminar flow is such a smooth and in a orderly fashion flow that even the determining the flow direction just by visualization is not possible if you do not have any float which is there. But turbulent flow, in case of turbulent flow, these things can be seen very easily, but turbulent flow are bad for the system, even for a river system, for a canal system, even for a pipe system. The more corrosion will occur in their case. So, the turbulent flow is the water particles or grains follow highly irregular circuitous paths and there is complex mixing of particles as also can seen in this figure. So, this makes the water mixing and violent kind of procession, and violent kind of procession will always give you the wrong or bad results, and this is what in our case is the erosion of bottom of the system or bottom of the your river or canal, even on the banks it will create problems. So, here again two examples are there about the vertical profile is shown about the laminar flow and turbulent flow. So, left side is showing laminar flow and right side is showing turbulent flow. Now, here the Vt and Bb and other things are also shown that the what happens to the friction between different layers in case of laminar flow. So, that top layer will have more velocity, in other words I can say, whereas the bottom layer will have less velocity, because bottom layer here in this case is having is touching the ground surface, that may be the sand or some clay particles or hard rocks in a real river system. So, the always water flows, the velocity of water at the top layer is the highest and slowly it reduces. So, this allows us to understand the system in much better fashion also. In case of turbulent flow, if there are undulations at the bottom, then the turbulent will be there, and these, as you can see that here the erosion will take place, here the depositions might take place. So, that means there are disturbances to the bottom of the system through which the water is flowing. If it is a canal or if it is a river, it will have erosion, it will remove the sediments from one place, will deposit another place. So, in a granular medium, because like when water flows through a channel, water may not be pure, it may have some particles, sand particles, or generally having clay particles if it is from long distance of the source. So, this granular medium, the different heads of particles are not entirely parallel and they are not in straight lines, as you can also see in this. In a definitely in turbulent flow, they are not in a straight line. So, that the rate of movement or overall the velocity in different parts of the pores having least near walls and the greatest in the center of the pores, being least in large intersections and greatest in the necks. So, this kind of situations will arise in case of also groundwater conditions. So, let me link with groundwater. So, if you increase the discharge, if you pump out water lot from a well which was not designed for that kind of output, what would happen? Near the where the pipe ends, your pump pipes ends, there will be turbulences in the water, and the result would be the damage to the well, and one day the well may become useless. That means you cannot further withdraw the water. So, that is why even a common man knows that if you run for a tube well for half an hour, give 2-3 hours rest and then again do it. So, the discharge should not be high, one, and replenishment time of water should be also given, so that the water comes through the surroundings into the well or near the well in the rock formations, and then you withdraw. But if you continuously withdrawing a high discharge, high Q from a tube well, then you are converting from laminar flow to turbulent flow, and you are basically damaging your well for good rather. So, this care has to be taken, that in no circumstances, I repeat, in no circumstances the water should not flow in turbulent manner in your well system. Now, we further discuss this part about the laminar flow and turbulent flow. So, like here that the velocity in a here it is shown through these arrows. So, you can see that it is more or less it is flowing in a smooth manner. However, after some time, if water is getting discharged from the bottom, after some time the velocity is higher. So, this curve is there which denote, and here velocity is low. So, all these arrow has been covered by this curve, and then turbulences are there, and therefore, in later on these velocity changes between different layers may not be there except at the bottom, where the friction by the bottom material is being caused. So, within a system, what I am trying to say, within a system, at some place the water may be laminar, at some place it can be turbulent, and some place it can be laminar again. But it will from converting a situation from turbulent to laminar, it will take time or distance. So, one has to be very careful or vigilant about this. So, this is what is the turbulent region, this is the buffer zone or buffer layer, and then this is the viscous sublayer where things are becoming more or less in a laminar fashion. Of course, this is not to the scale. So, the first part is showing your laminar flow, as you can see between this to this. The second part is the transition between laminar to turbulent, and the next part is the turbulent flow, which you can see. So, regardless of these differences between laminar and turbulent, laminar flow is the orderly to the extent that there is not mixing of particles between adjacent threads of flow. So, if this is there, as long as these conditions are there, the flow will remain laminar. So, in laminar flow, the velocity is proportional to the first power of hydraulic gradient, and Darcy law is therefore applicable. This I also said few minutes before, that Darcy law is only applicable in case of laminar flow. As soon as your flow becomes turbulent, then Darcy law cannot be used to estimate the Q or other parameters. So, in turbulent, water particles flows highly irregular, non-orderly fashion and circuitous paths, and there is complex mixing of water particles, and laminar flow generally occurs at a low velocity and turbulent flow at high velocity. So, if the discharge is maintained to the optimum, you would have laminar flow in your well, and there will not be much problem later on. So, in laminar flow, the fluid particles, as we have already discussed, move very smoothly, more or less in the same direction at the bulk of the fluid, and whereas in case of turbulent flow, the motion of fluid particles at any point can be changing rapidly both in speed and direction. So, if you go in and observe in open systems, open channel systems like in river or other things, even if I take the stretch of Ganges, even in the hilly regions where the this head loss is quite big, even in such situations you may find stretches where the water in the Ganges is flowing or in tributaries are flowing in a completely laminar fashion, and where at other places there might be turbulent. So, where are the turbulent, more erosion is taking place and deposition will take place where the things become laminar. So, laminar flow, the viscous forces are dominant, they are controlling basically this orderly fashion of movement of water, and that is the fluid is tending to resist motion of its particles relative to each other and maintaining a laminar flow. Whereas, in case of turbulent flow, the viscous forces are being overcome and the particles are whirling around in a much more unruly fashion, unordered fashion. So, laminar flow typically occurs when fluid is moving very slowly through small openings, that is capillary tubes or very thin sheets. Turbulent flow can occur where steep hydraulic gradient exists. So, if the slopes are gentle and bottom is not rough, channel is straight, more likely you would have a laminar flow. But if these conditions are not there, you might have a turbulent flow, high hydraulic gradient. So, near pump wells, this example I was giving. So, that near pump wells, rocks as site like igneous rock like basalt or sedimentary rock like limestone, which contains large underground openings and cavities. So, these can create turbulences in that part. So, if your pump is ending or the pipe of that pump is ending in a cavity or openings which is very large, then you may have sometime a turbulent flow. So, the better always is to maintain the Q to a minimum or optimum level. So, most groundwater movement is relatively slow and therefore laminar. So, we try always when we do withdraw water that what in any condition the withdrawal should not create turbulences in the at the bottom of the well. So, if we maintain a very slow, we will have a laminar. So, exception of course occurs when water moves through caverns or enters a heavily pumped well. Heavily pumped wells means you are taking too much water continuously from a well and trying to convert, or it will get converted from laminar to turbulent flow. So, these are the some lab experiment through which you can see that how these turbulent flow or swirling or whirling occurs, that the irregular flow paths of eddies and swirls associated with turbulent flow occurs first in the larger pore spaces with increasing velocity as they spread to the smaller pore spaces. So, this eddy is swirling of fluid and reverse current created when the fluid is in turbulent flow, and while the swirl is the whirling eddies. This we can see here, the experiment we have done, different colors have been injected and these things you can see. So, here we are ending this part 2 of Darcy law. In this we mainly focus on laminar flow and turbulent flow and different conditions. So, in the last part of Darcy law we will be discussing further about what other parameters influences our Darcy law and how much it is applicable, where it is valid. So, for this time being, thank you very much.